Good morning, class, and welcome to Chapter 4. Today we're going to start out by looking at Section 4.1, maximums and minimum values. The good news is today we're going to look at graphs. Tomorrow we're going to go ahead and look at how you find maximums and minimums using calculus. So the first thing we have to look at is the definition for an absolute maximum. If we're talking about an absolute maximum, it means the absolutely biggest number, biggest y value, I should say, on a graph that we can find. So a function has an absolute maximum. Some textbooks also call it a global maximum. At a point C, if f of c is greater than or equal to f of x. Okay. What this is saying is we have a point C where all the y values are bigger than every other y value around, okay, in that interval. For x in domain D, where D is the domain, the number f of c is called the maximum value of f on D. And then the same thing for a minimum. Okay, so if you have the smallest y value compared to every other y value in the domain, then f of c is your absolute minimum. Okay. The other thing that we have is maximum and minimum values are called extreme values, which makes sense because if you are the extreme value, you're either high or you're low. Okay, so we're looking at those. So I have a graph here, and we are going to but we're going to determine which ones are absolute max and absolute min. So I look here. I see this is the highest point on my graph. So this is my absolute maximum. It is the absolutely biggest point. Then I go ahead and I look, well, what's my smallest y value? And I would see right here. And so this would be my absolute minimum. Okay. So those are our absolute max and our absolute mins. Now we also have what we call local max and mins and relative max and mins. And I meant to have this one still on our picture from before, so I'm actually going to copy this definition really quickly. All right, we can look at it over top. The other one is the local max and the local mins. So what the locals are they are values that are the biggest around the x value you're looking at. So if I look at this point right here, do you see how when I look to the left and look to the right, it is the highest value locally? That's why this one is called a local max. Okay, so that's what we talk about when we talk about local. Some textbooks also call it a relative max. The same thing can happen for a local min. Do you guys see how this is our lowest point with what's around it? So this is a local min. Then I go ahead and I look at this point. It is an absolute, but it's also the highest for what's around it, so it is also called a local max. Then we would look here. This is a low point compared to what I'm around, so this is a local min. And then I get to my end point here, because this is really like a closed circle, okay? Endpoints cannot be local max and mins. So you might probably want to write this down. Local max or mins cannot be endpoints of an interval. The reason they can't be is, you see how you can't check to the left or the like on this case, you can't check to the left. To be local, you have to be able to look left and right to make sure it's the highest or lowest point for what's around it. Same thing here. I can't look what's going on over here, so I don't know if locally it actually is a max or min. So that is everything in terms of, you know, our absolutes are our highest and our lowest, and then locals are as long as they are the high point for what's around it or the low point for what's near it. So there is that definition. We have a function here. So here's our example one. The function y equals cosine of x takes on local and absolute maximum minimum values at 1 and -1. Okay, so if you guys look here and here, they have the same highest value. So all this is showing is graphically the absolute max of cosine is not -1, +1 is 1. and our absolute min would be -1 because that's our smallest y value. The biggest thing to take away from the cosine function is, can you have multiple absolute maximums? Yes, you're going to have in this case, because cosine will continue to go on like this pattern, you'll have multiple absolute maximum values and you will have multiple absolute minimum values. And that's okay as long as they are the biggest number together. So like they're all a high value of 1. These are all a low value of -1. So anywhere there is a y value of -1 on cosine, that's an absolute min. Okay. Another picture we have to look at is y equals x squared. Okay, if we look at this one is really trying to say that we have arrows going on. Does this one have an absolute max or an absolute min? Or neither? So I go ahead and look. This one, this is the lowest point, so this is our absolute minimum. Would it also be a local? Yes, it would be, because locally it is the smallest and a local min. And now, would it have an absolute maximum? It would not, because these are going to continue to go up and up and up. So you would not be able to say, well, this is my highest y value, because it's going to continue on to infinity. So in this case, there is no absolute max. Example 3. Go ahead and look at example 3. And this one is a case where there is no extreme values. There is no absolute maxes or mins. So no extreme values. Now why? These continue to go up and up, so I can't say this is my lowest value and this is my highest value. And if I look here, we see something's going on, but is it the highest for what's around it? No, this would have to go down to be like an absolute max here. So there is no absolute maximums or absolute minimums on x to the third. All right, example 4, below is the graph, and it is sketched here from -1 to 4. So they're saying they're closed points on the end, so we have endpoints. Remember, endpoints cannot be local max and mins, but it says find all absolute maximums or minimums and any local maximums or minimums. So let's start out with the absolute max. Who is the very biggest point or the very highest point? Right here. So it's -1, 37. Okay. Then let's go ahead and find our absolute minimum. Where is the lowest point? 3, -27. That's our absolute minimum. Now we have to go ahead and do our local maxes and our local mins. Okay, so we got local max. So remember, locals cannot be endpoints, so I'm going to ignore those two. But right here, would this be a max or a min? That would be a local min. How about here? That one would be a local max. We'd have 1, 5. This would be a local max. And I think, sorry, that'd be a local min, not a local max. I think that will be it for our local maxes. There's just the one. Okay. Then let's go ahead and write down our local minimums. So here would be a minimum, which is the point 0, 0. It is the lowest for what is around it. Then here's our max. Here is our min, and it's an absolute, but it is also a local. So there's actually 2 locals. Okay. So that is it for example 4. The first few problems on your homework today, you're going to have to write out what's the absolute max, mins, locals. So something very similar to this. The extreme value theorem. It is a theorem that is helpful to make sure you can say, I have an absolute max or I have an absolute min. So if a function f is continuous, remember continuous means you can draw it without picking up your pencil, and on the closed interval from a to b, that means it has closed endpoints. See how this one has closed endpoints? Then f attains an absolute maximum value, f of c, and an absolute minimum value. They're saying this has to happen. The reason is because you can have your endpoints be absolute max and absolute mins. Okay? So if I look at this example here, where is my absolute maximum? Here is my highest point, so the point would be c, comma. Now how would I figure out my y value? The way we'd write it, we don't know the function, but you'd plug c into your f of x function, so f of c. Then my absolute minimum, in this case it's d, comma, f of d. Okay? But every time that you have a continuous function with closed intervals, you will have a max and a min, an absolute max and min. If I go ahead and look at this next example, the absolute max. This is my highest point, so it's c comma f of c, because that's how you get your y value. And then your absolute min, my lowest point. Looks like this is my lowest point. I'm just going to use that this is b. So it'd be b comma f of b. There we go. Good. Okay, so that's our extreme value theorem. So in order to use the extreme value theorem, a function must be continuous. So maybe some things we should remember is what makes it continuous. I would say in order to be continuous, you can draw and not have to pick up your pencil. Okay, so things we got to be worried about are asymptotes, holes, and jumps. So how do we make sure that this happens? Well, it means that if this curve is on here, and let's say that this is point A, the limit as you approach A from the left and the right has to exist. So our limit as x approaches A of f of x, I'm going to call this function f of x, must exist. And in order to exist, remember, the left and the right-hand sides have to be the same. Then the next thing is that f of a, the point, must exist as well. And it must be a filled-in point, and so my limit, as it comes from the left and the right, is equal to the point. So we have the limit as x approaches a of f of x must equal f of a. So we did some proofs showing that things had to be continuous, and this is how you would prove that things must be continuous. Okay, today we're looking at graphs, so the biggest thing you need to take away is remember when you draw it, you don't pick up your pencil at all. There's no holes, there's no asymptotes, there's no jumps. Okay. So we're using the extreme value theorem to find the absolute max and absolute min. So in order to use the extreme value theorem, okay, you got to be continuous. So is this one continuous from A to B? Yes, I do not pick up my pencil, so yes. And then the other thing we have to make sure is, are we on a closed interval? So to be on a closed interval, you're going from one point to the next, and they are closed endpoints. Okay. And in this case, we are. Our closed interval is bracket A to B. So what this tells me is that there will be an absolute max and there will be an absolute min because that is the case. Okay. So looking here, absolute maximum. This is my highest point, and if you ask me, they are the same y value, so I really have two absolute maximums. So we have c sub 1, comma, f of c sub 1. Okay, and we also have c sub 2. C sub 2 and f of c sub 2. Those are my absolute maximums. Then my minimum is my lowest point, which looks like it's here. So that is d comma f of d. Use the extreme value theorem to find the absolute max and absolute min. So same thing, we got to check. Is it continuous? Whoa, can't spell. Continuous. No, it's not. It is not continuous. So what does this tell me? This tells me there doesn't have to be a max and there doesn't have to be a min. Can there be? Yes, there can be, but there doesn't have to be, okay? So since it's not, there won't necessarily be both of these. So will there be an absolute max? I see that this is my highest point. However, do you guys see how it's an open circle? Since it's an open circle, I can't claim that it is the absolute maximum. So there is not one. No. None. Probably no. None's a better way to say that. None. And it's because it is not closed at x equals 1. Okay. And then is there an absolute minimum? Well, the lowest value is here, and yes, it's closed, so yes, there is. It would be 2, 0. Okay. So the extreme value theorem doesn't apply in this situation because it's not continuous. But if you are continuous on a closed interval, you will have an absolute max and an absolute min answer every single time. All right, same thing, use the extreme value theorem to find that it is an absolute max and absolute min. So first things first, is it continuous? Yeah, I don't pick up my pencil, so I would say yes. However, is it a closed interval? Well, it's an open circle, so no. And if I check down this side, it's an asymptote, so no. So it's a 0 to 2. So no, it's not closed. So then I would go ahead and look. Is there an absolute max? I go to find this. This tells me I'm going to approach my asymptote and continue to go up and up and up. So could I really put a definite number on my highest y value? No. So that's why there is no absolute maximum. And then absolute minimum. I go to write this down, however, it's not included. And I can't say, oh, it's the one right next to it. Okay, this is it, and since it's open, there is not one of those either. So for Mots theorem, we're going to get into this a little bit more. But if f has a local max or minimum, and if the derivative at c exists, then the derivative of function f at c is equal to 0. We've graphed derivatives before, so basically we have to take here and take this into account. Do you guys see how the slope here is equal to 0? And in calculus, you guys know that slope of a tangent line at a max or min or a turning point is 0. Okay, so these are where your extreme values occur. It's either going to be your highest or lowest relative max or local max or min, and then your absolute. So this is one way we can use calculus to find where these extreme values are going to occur. Another place or another way we can find where extreme values occur is where the derivative fails to exist. Okay, so we have to think about, well, where do derivatives fail to exist? So let's look at this graphically, or think about it graphically. One way is that it is discontinuous. If you're discontinuous, your derivative does not exist. Your other one, the one that you guys usually come up with quickest, is your corner or your cusp. Okay, so something that looks like this. Their derivative does not exist here. And then the last one, you guys forget about a little bit, but it's your vertical tangent. So if I have a curve that kind of looks like this, oh, this isn't very good. Right here, I would have a vertical tangent. So that's where my derivative does not exist. And we all know what discontinuous looks like. It might look like this and have a jump. It could be an asymptote, that kind of stuff. So that's where your derivative fails to exist. But tomorrow when we're looking at calculus, or the calculus aspect of this, is in order to find maximums and minimums, it's where your first derivative is set equal to 0. Okay, because you have slopes of 0, which looks like high points and low points, and also where your derivative fails to exist is where you can have a maximum or a minimum. So the way your derivative exists is when you're discontinuous, you have corners, or you have that vertical tangent. Okay. All right, you have a few of these on your homework. It's kind of fun to have you guys do them in class because you can come up with all kinds of different options. But I guess with the flex day today, we will just go ahead and I will give you some options. But it says sketch the graph of a function from -1 to 2 that has an absolute max, but no local minimum. Or sorry, no local max. We have an absolute, but no local. Okay, well, let's think about it. Well, if I have a max and I have no local, what did I tell you guys locals could not be? Locals cannot be endpoints. So I'm going to have to draw something that has an absolute max that's an endpoint, okay, on that interval. So I'm going to sketch it. We got -1, 1. Let's see. Closed interval. Here's an option. We would have a max at x equals 2. I could have also did it the opposite way. Could have went this way. But there's an option. Is there another thing I could have drawn? I think so. We got -1. There's usually at least more than one option you could always have. What if I did this? This is the absolute minimum and a local minimum, but it's not we can't have just no local max, so we're okay here. Yep, so here would be my local max. Sorry, not local. That's your absolute max. This is your local and absolute min. And then this would be nothing. So there it is. So there's two options of an example that has this case. Last one, sketch something on the interval from -1 to 2 that has a local max but does not have an absolute max. Okay, so we're going to have something like that. Think about how that could occur. One option would be that I have maybe a jump. Okay, let's think. If I go okay, no absolute max. So it's open circle. That'd be my highest point, so I'm not going to have an absolute max. But do I have a local max? Yes. Here would be my local max. What would this one be? It's an endpoint, so it can't be any locals, but it is these lowest points. So this is your absolute min. But there would be one option that you could have. Another option for this case is something along the lines of technically closed interval. I'm looking from -1 to 2, and I got closed points on it. And then does it have a local max? This would be my local max. But it is not the biggest point, so there is no absolute, because that's not a closed circle. So is that. This one right here would be, what would that be? It's a local min. And this endpoint right here would be your absolute min. Okay, but it's just making sure it meets the criteria. We have a local max, but no absolute min. And I'm going to give you guys one more option that you could think about, and then we'll just maybe take note of what they all kind of have in common. Ooh, I kind of squeezed it on room. There we go. Maybe I did something like that. These are going to continue to go up. However, right here would be a local max. It looks like here, if I would have drawn that a little more straight, these look like they could be both absolute mins if they're exactly the same. But biggest thing is it has no absolute max, and it does have a local max. So what is something in order to make this situation happen that I had to have? I had to have discontinuous, right? We were discontinuous here. We were discontinuous here. Discontinuous here. Okay, that was one option. So I would take any of these answers. There are lots of ways to draw them, but there is that. So your homework, 3 through 9 all, 15 through 27 odd. So 3 and 4, you're just going to write down if it's a local max or local min. That should be pretty straightforward. Same thing here, absolute and local max and min values. Then here's where you got to do a little sketching, same as we just did on example 8 and 9. And then this one, it says sketch the graph by hand and use your sketch to find the absolute and local max and min. So this is what I want to talk about. This one is looking at the line. What you can do is you can graph it on your calculator if you want to. But this is a line with the y-intercept. I'm just going to roughly sketch. Okay, with a y-intercept of 8, and then we're going to go down 3 to the right 1. I don't know if I'm exactly getting this right, but we got the idea. So, but we're only looking at it for x greater than -1. So, or sorry, greater than 1. So I'd really only be looking at that part of the graph, and it says greater than, so there's really an arrow on here. Okay, this is for 15. And then it says, find the absolute and local max and min values. So looking at this one, we're only looking for x bigger than 1 and going this way. And since it's bigger, we continue an arrow here. So will this one have a minimum? No, because it's going to continue on. But I do have an absolute max. And it'd be 1 comma, when I plug in 1 to here, I get out 5. So that'd be your answer for number 15. Okay. Then we're doing all the odds. So then you move to 17. 17 is a parabola. You're looking at it from 0 to 2. So when I plug in 0, I get out 0. When I plug out 1, I get 1. And then when you plug in 2, you get 4. And they're open circles. But you could graph this on your calculator. Or you can just sketch it. Either way. So what does this one have? It has open circles. So I have absolutely no absolute max. But I do have this right here. So this would be a local min and your absolute min. And it would be the 0.00. So that's what you would do. Then you do the same thing for 19. Okay. So these are all pretty straightforward. Put them into your calculator and graph them. And then this one is your good old piecewise. So give that one a try. Hopefully your assignment goes pretty quickly. I hope you have a good day. Talk to you later. See you tomorrow. Bye.